All right, cool. We're live here. So yeah, first off, I messed up yesterday and I recorded the wrong desktop during the lecture, so that whole video is gone. But we're going to go over linked lists again today, kind of from beginning to end. You've seen it, once in class, so that will help. But I want to go through, kind of the whole story of linked lists. And then I want to jump into PA1 and use that to talk about coding aspects of making linked lists and, in particular, programming assignment 1. So any questions before we get going on all that? All right, cool. Let's just hop into it then. So let me start this by looking at lists in terms of pictures, and let's suppose we're making a list of numbers. So 12, 24, 30. We want to store 3 numbers in this structure. Could we go over the main.c for ODP 202? So main.c is totally up to you. If you want to work on, so let me tag this. If you want to do your own test program, which I recommend, right, make yourself a main.c. Declare a struct node, right? Define that, because your code needs to know what a struct node looks like. And then in your main program, make an array. Call it whatever you want, right? But make an array of struct node data bracket 100, and then call your init function just by saying init, name of the array. And then either run this in GDB and use the print command in there, or use printf to somehow look at the contents of your data array, right? So I don't know, make a loop from 0 to 99 maybe, and print out data bracket whatever index you're looking at, dot whatever fields you're interested in. And yes, you can always assume that you've got 100 elements. So if you want to test this in your main, I would just print out all 100 elements, formatted nicely, and just look at it and see if everything's initialized correctly. Or run it in GDB, and when you come back from init, have a breakpoint and start using the print command to look at the elements in your data array. To go like that. What do you mean the whole list printed 3 times, even with the proper test bed? Did you ask it to print 3 times? And I didn't adjust the canvas date, but don't worry about the canvas date. The ODP is still up and running, so you've got until tomorrow morning for that. So on Canvas, I just put the date up for you to know. But yeah, you've got an extra day on it. When you link with a test bed, don't run the test bed program yourself. Just run it through the assess command. Because if you just try to run the command that you've linked with the test bed, there's a good chance it'll seg fault or it'll print weird things. Don't worry about that, right? The test bed is strictly for turning into the assess function. And sometimes it deliberately, does strange things. to discourage reverse engineering. Yep, init.c is a function that populates struct node. Yeah, init.c has the init function, and that's all that should be in there, plus, you know, the declaration of a struct node. Make sure you declare the fields in the same order as shown in the assignment. Make sure you do all the initializations in the assignment. Make sure that you initialize elements 1 through 99 inclusive. Right, you got to get all 99 of those set up. The order matters because when we compile our code and we assemble it and we turn it into binary, those field names are gone, right? There's nothing in the executable that says, you know, this is the data field, this is the next field. They're simply displacements from the beginning of the structure in memory. So the compiler will decide, okay, so if you have a variable of type struct node called x, x will be the address of the data part, and then x plus 4 will be the valid part, and x plus 8 will be the next part. And if you define your structure with the things listed in a different order, then the order of those in memory may be different. And the test bed is already compiled, so it's already decided, you know, the beginning of the structure is the data part, followed by the valid part, followed by the next part, and so on. So changing the order in your code will actually cause it to pick up the wrong fields from memory. It's one of the ways in which C code is considered, you know, potentially error prone compared to something like, you know, an object-oriented language. All right, so let's do some linked list pictures. And let's do our list. Suppose we're doing a 12 and a 24 and a 30 in our list. And so the idea is we have these nodes. And they could be anywhere in memory, right? They're no longer required to be sequential. But each node contains a piece of data, right? The thing that we're trying to store, as well as a field that we think of as a pointer to the next thing in the list. So our list begins with a 12, that points to a 24, that points to a 30, and a 30, the next field would be my null, indicating that there's nothing else after that node. That's the end of the list. And if you want to insert, I don't know, a 26, well, we do 4 things. First, we create a new node somewhere containing a 26. That's the first step. Second step, figure out where this should go in the list. Should it go before this, after this, or somewhere in between? And for inserting and keeping things in order, we do the following. We look at the first node. That's less than 26, so 26 is going to go after this. So go on to the next node, 24. 26 is bigger than 24, it's going to go after this node. We go to the next node, 30. 30 is bigger than 26, so 26 should go before 30. But we know it went after the previous node, so it's got to go in between this node and that node. So you have to find where your node should go in memory in this list. And so I'm going to have a label on this. This was the last index. This was the current index. Those are just names I'm putting on these nodes. And I want my new node to go in between this node and that node. Okay, so second thing, figure out where your node should go. Third thing, change your last index to point to your new node. And fourth thing, have your new node point to what I called current index, the first node that was bigger. And that's it, you're done. You've inserted into this list. All right. If you want to delete, let's say we want to delete the 24. Well, again, we have to start off from the beginning of the list, and we have to look for the node we're trying to delete. Well, that's not what we want to delete. Let's follow it. There's a 24. Hey, that's what we want to delete. Okay. But here again, we need to keep track of the previous node. So I would say this was last index, and this is current index. All right, because once we get to the node that we want to delete, we need to know the node that's pointing to it. And the whole deletion is just going to be take this node and point wherever this node's pointing. That's how we're going to delete the 24. Have the 12 point to whatever 24 points to. But we don't know that it's this node that's going to be adjusted until we've gone past it and gotten to the 24. So we always need a pair of pointers. As we're moving through our list looking for something, a place to insert, a node to delete, we're always going to want a pair of pointers that are going to move in lockstep. So when we get to the action point, we know what the previous node was. All right, so in this case, I'm deleting 24. Well, I got to 24. I know the previous node was right here. How do I do the deletion? Just take the previous node and change it so that it points wherever the current node points, right here. There you go, you're done. All right, so use a pair of pointers marching through. So memory does not get cleared here, right? Even though I've removed this node from the list, it's still sitting in memory somewhere. And that's where we get into, you know, the issue of memory leaks. So we'll have to deal with that, but that's going to be a small detail in PA1. It'll be a bigger detail in PA2, but still easy to take care of if we're careful. All right, so let's see. Why not just have each node also have a pointer to the last node? What last node? Because the last node, by last node I mean the previous node as I'm going through the list. So let's think of it like this. Let's suppose I have a 10, points to a 20, points to a 25, points to a 36, points to a 47, points to a 48, points to a 95. And suppose my list starts here. And suppose I want to delete 47. Well, I have to find the 47 in the list first of all, and the only way I do that is by starting with the first node. Not 47, nope, nope, nope. Yes, ding, 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 there's my 47. Okay, if I'm just doing that by, moving through, looking from node to node, I've lost a piece of information, because to delete this 47, I need to know what was the node I was just at before I got here. I need to know the identity of this node so I can change this thing's next field to point to 48. So this is what I mean by a pair of pointers. When I'm going through the list, instead of just saying, nope, 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 yes, there's my 47, I'm going to have a pair of pointers. Nope, 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 yes, there's my 47. My previous pointer, what I'm calling my last node, is going to point to the 36. All right? And so it's just a matter of keeping track. If 20 is not the node I want, I'm going to change, last index to 20 and current index to 25. Nope, 25 is not what I want. I'll change last to 25, current to 36. 36 is not what I want. I'll change last to 36, current to 47. Hey, 47, that's the node I'm trying to delete. Well, guess what? My last index is pointing to this 36. That's all I need. right? As long as I know the identity of this node, I can adjust it to point to whatever 47 is pointing to, and that'll let me do my deletion. All right, so somebody just brought up a good point in chat. What if we want to delete the first node? What if we want to get rid of this 12? So let me get rid of these labels here. Those are just temporary variables. But suppose this is what our list looks like. We've got a 12 going to a 26 going to a 30, and we want to delete the 12. Well, you know, to delete, we need the previous node to point to 26 in this case. Well, there is no previous node. So, okay, I've deleted a 12. Well, how do I know that the 12 is not part of the list? Every time that we've done something in the past few minutes with this list, we always started right here. Why did I start here? Because this is the upper left corner, right? But if we're deleting the 12 from the list, now I need to know, hey, my list starts down here. Well, how do I know that? So you need some kind of, you know, big blue bubble that sits there on your first node. There's a big blue bubble that sits there on your first node and says, this is the beginning of my list. So, you know, normally it's out there, and then if I delete the 12, I'll change that to be right here. And that's a pain. So we use a trick. Okay, and the trick is to use a sentinel node. And yeah, this will be element 0 in our array. We'll switch to the array in a moment. So the trick is we always have an extra node, which is called the sentinel. And we don't use its data value, but we use its next field to point to the first node of our linked list. So even though we're going to start from here with this node when we do anything with the list, this is not part of the list. This is simply a pointer to the first node in the list. Okay, it's like a bogus node. So everything we've done so far, we want to find a 30, right? Well, we'll start with a sentinel. That points us to our first node. Nope, that's not a 30. Nope, that's not a 30. Hey, there's a 30. I found a 30. Okay. But now, if we want to delete the 12, what happens? Well, we're going to start off with a sentinel node in the first node, and this is going to initially be our last index. And this is going to be our current index. And we're trying to delete a 12, we check current index, hey, there's the thing we want to delete. Well, the algorithm is exactly the same as we did a few minutes ago. Take the previous node, which is last index, and just change it to point wherever the current index points. That's right down here. We've deleted the 12. How do we know? Well, let's see what's in the list. Start at the sentinel, that points to our first node is a 26. That points to the next node is a 30, and that's the end of the list. So the sentinel is a nice trick that stops us from having to have something that, you know, tells us where our list begins. The sentinel is basically a pointer to the start of the list. But because the sentinel is not part of the list itself, it never changes. It never goes away. It never gets deleted. It never gets anything inserted before it. So it's got a fixed location, and we can hardwire that. And that's actually going to be what we can think of as our handle to our linked list. That's the thing we can pass around. All right. So let's talk about how we do this using an array, which is what programming assignment 1 is all about. Let's see, do you always support a sentinel as opposed to something like a head node? So a sentinel is a head node. Basically, the way I use the term head node is, or header node is, that's basically a sentinel. And it you know, it takes one extra node in memory, but usually it's a win-win situation. But when we get to other data structures like trees, we're not going to have a sentinel. The disadvantage of a sentinel is that our linked list looks different from a sublist. This is getting into a little bit of fine-grained detail. But if this is a sentinel node, right? If I were to try to make a sublist that started from the 15, my code won't work with that because I don't have a sentinel node in front of this. And that's the reason that we won't use sentinel nodes on our lists that turn into binary trees. But we'll see that in a couple of weeks. You're welcome. All right, so how do we do this in an array? And we're going to use an array for our linked lists for programming assignment 1. So let's make an array. And this is going to be an array of struct nodes. And just like in the ODP, our struct node is going to have 3 fields, which we'll call data, next, and valid. And it's just a plain old array. Everything is indexed, everything is sequential. Nothing funny going on. So I'll put some indices next to here. And so let's suppose we've got our list containing a 12 and a 24 and a 30. All right. Now this box up here, this is always the sentinel node, so this is not technically part of our list. And basically, you know, if we think of our linked list in terms of pictures, here's what a node looks like. It has a data field, and it has a next field. And the next, we're drawing arrows to point to the next node on paper. But if we implement this in an array, these next values are going to be indices. And this is going to have the index of the next node in this array. So let me call this array LL for linked list, or Lucky Louie, or whatever you like. All right, don't worry about the valid flag yet. So our data is going to get stored in the data columns, and next to each piece of data is going to be an index where the next node from our list appears. All right, so let's start looking at PA1 in parallel with this. So PA1, you're doing 2 things. You're creating a linked list, right, an implementation of a linked list using an array. Hold on, let me do this. You're creating an implementation of a linked list using an array. You're writing a set of functions that can be used to manipulate that list. And then you're writing a main program to take commands from a user and let them do things with their linked list. Add things, search for things, delete things. Okay, so a bunch of different pieces to this, but let's look at the mechanics of the linked list itself. So your list is going to be an array of struct nodes, where a node is defined as a structure containing 3 integers called data, next, and valid. This should sound familiar. This is ODP 202. Okay. Data is going to be the integer we're storing in our list. Next is going to be the index in the array of the next element. Or, if you hit the end of the list, we're going to use this variable called myNull. It's going to be a 0. Right? And since all the data in our list is stored somewhere from elements 1 through 99, if we have something which says the next element is at index 0, we know that's not actually pointing to an element. So we're using 0 in the next field as a flag to say that's the end of the list. And valid is going to tell us whether or not an entry in our array is actually part of the list. And we'll see how we use that in a little bit. Okay. Now in ODP 202, I had you initialize the data, next, and valid fields to totally bizarre, arbitrary, random values. Okay, 42 and -17 and all that stuff. Totally random. I just made that up to make it interesting. Okay? Nothing to do with the actual values we'll want to use in programming assignment 1. But the structure of the array, the fields in the struct node, those are the same. Okay? When you use a value of 0 to say that there's nothing else in the list, I do not want you to code a 0. I want you to make a symbol called myNull by using a define statement, and always use myNull. So if you're going through your list and you want to know, did you get to the end of the list, don't check to see if the next field is equal to 0. See if it's equal to myNull. Okay, that's just a little detail, but it's important for PA2, and there's actually point value in using myNull instead of 0. The valid field, that's just a 1 or a 0, so you just use a 1 or a 0 there. Don't use null for that. Okay, your linked list itself should be declared in your main program as an array of 100 struct nodes. That should also sound familiar. If you wrote a test program for ODP202, that's your main program's array. And so this is a linked list that can hold 99 data nodes, and index 0 is special. That's going to be the sentinel node. All right, so how do I want this to be initialized? You're going to have an init function, kind of like what you already wrote for 202 or will write for 202. Okay, the init function should create an empty list, which means there's a sentinel node and it points to myNull. So empty list is at index 0. The next field should be myNull. And then all the other entries in your array should have a valid flag set to 0. So here's what your init function should do. It should set this to myNull. And it should set all of these fields to 0. So null is actually a pointer to 0, but we're going to make our own symbol called myNull. Just make it an integer. Set it equal to 0. And it's going to be replaced by null in PA2. All right, we don't care what the data field is in the sentinel. We don't care what the valid field is in the sentinel. Okay, this is a special node. It's not part of the linked list. All we care about in here is this next field, and that should be initialized to myNull. So what do we know about our linked list right now? Well, what's in our list? Well, what's the first node? There is no first node, so our list is empty. The other thing we know is all 99 of these locations are not being used. They're all available for future use. Okay, that's a fully initialized empty linked list. And your init function for PA1 should set up that initialization. So it will look almost exactly like ODP202's init function, except instead of using bizarre values like 42 and -17, you'll set up these values as defined in PA1. Okay, what would data look like in this array corresponding to a linked list? Let's imagine our linked list containing a 12, a 24, and a 30. And here's a sentinel. So suppose we're starting with a linked list. And our sentinel points to 12, 12 points to 24, 24 points to 30, 30 points to myNull. So that's the end of the list. Let's see, question, you prefer our functions are written in one file, or do you want them written in separate files in a make file to compile them? It's up to you. Either way is fine. Did I ask you for a make file? I hope I did, and I think I didn't. A make file, good. Okay, cool. Yeah, so you can break them into files however you choose, as long as I have a make file that will build them. All right, so let's suppose this is our list. Sentinel points to 12, 24, 30. What might this look like in our linked list array? Well, it could look a lot of different ways, but let me just show you one possibility. So maybe we inserted these nodes in order to begin with. And so maybe this is our 12 and our 24 and our 30. which means each of these is going to have a valid field of 1. The sentinel is going to point to the first node at index 1. 12 points to the second node at index 2. 24 points to the third node at index 3. And the 30 has a next field of my_null. So this is almost verbatim this picture, except that instead of arrows, I have an index number for the next node. So those arrows are basically captured by the value of this next field. Okay, and suppose the user wants to insert a 25. All right, we're going to use a pair of pointers to find where we want to insert. Now, where do we want to insert a 25? The first spot where a node is bigger than 25. Right? 25 is bigger than 12, but that doesn't mean that it goes right here. 25 is bigger than 24. That doesn't mean that it goes right here. The only way you know where to insert it is you keep going until you find the first node that's bigger than this. So 12 is smaller, 24 is smaller. 30 is bigger than 25. So we want to insert right before this node. But again, in order to do that, we need to modify this previous node. So we're going to have a pair of pointers. And we're going to start off with, let me just call this previous and current. All right. So start off, let's look at the 12. 12 is not bigger than 25. So we're going to insert somewhere after this. Okay, I need to move down the list. So I'm going to change current to be this node, but before I do that, I'm going to change previous to be current. Now I look at 24. Nope, 24 is still smaller than 25. Let's move down again. Right, so set my previous to my current, set my current to the next node. Let's look at the 30. 30 is bigger than 25. This must be the node I want to insert before. And guess what? My previous value is pointing to the node I want to insert after. So I know I want to put my new node in between previous and current. All right, so how do we do this? Let's insert the 25 after previous and before current. Now, if we're doing this in our linked list, our previous is going to be the index of the 24 node, that's a 2. Our current is going to be the index of the 30 node, that's a 3. So we want to insert between the 2 and the 3. All right, we're going to do this in 3 contexts. We're going to do this on the picture, we're going to do this in the array, and we're going to write code. And the goal, this is the most critical next few minutes of the whole quarter, okay? The whole goal of this is to understand how we want the structure to be modified. That's what our picture is going to help us with. And then to figure out how we want memory to be modified to correspond to those changes to our structure. And once we know how we want memory to be modified, then we can write some code to do that modification. Now in this case, you know, our memory is an array. In PA2, our memory is going to be a dynamically allocated data structure. But the process is the same. And we're going to end up with some C code that will insert a new node in between 24 and 30. I don't want you to fall in love with that C code. Okay, that C code by itself is not worth anything. The real nugget here is knowing how we want to update this picture and then thinking about how memory should be modified to correspond to that update. And once we know that, the C code almost writes itself. Okay, so this is our golden nugget. Our end nugget. So let me say it again, and then we'll go ahead and do it. Okay? We're going to think about how we want our structure to be modified, which is going to be, we want a new box containing a 25. We want this to point to the 25. We want 25 to point to 30. And then we're going to think about how should memory be modified to implement that change, to achieve that change. And that's what we've really got to figure out. Once we know what steps should be performed, we can write some C code. But the C code is trivial to write once you understand that. The challenge is not writing the C code. The challenge is figuring out what we want the C code to do. After that, it's 2 assignment statements. But those assignment statements are going to have lots of complexities in them. And knowing how to fill in those complexities by looking at the C code, hopeless, right? Figure out how to write the C from thinking about your memory. Okay, that's the essence of data structures, which is 222, 223 university programming. All right, so this is the magic part. Okay, what my fiance calls the goods. This is the goods. All right, let's do the picture first. So we're going to create a new node with a value of 25. Okay, what should that look like in our array? Well, we're going to put a 25 somewhere in here. But where is it going to go? Well, we don't want to put it here because we're using that for our 12. How do we know we're using that? Because it's got a 1 in the valid field. Same with 24, same with 30. In memory, these are not empty boxes. In memory, these all have values in them. I don't know what they are. They're big, long negative numbers or positive numbers. So you and I can look at this and say, oh yeah, that's the next empty location. We'll put it at index 4. But how are we going to tell the computer to do that? Well, this is what the valid field is for. Basically, we can start with index 1 and find the first spot where the valid field is 0. Wherever that happens, that's the index we're going to use. All right, so you're going to write a function to do that. And your function is going to be called getNode. This looks for the next free spot in the linked list array by checking the valid field of each entry. All right. So we can do this on paper pretty easily, right? Start from index 1. Index 0, don't use the valid field. 0 is the sentinel node. But let's start from index 1. Valid is 1, valid is 1, valid is 1. Hey, valid is a 0. Okay. So I'm going to do three things. I'm going to set the valid flag to 1. I'm going to record the index of this node, and I'm just going to call this new. And then I'm going to set the data field equal to the number I'm inserting. So I'm going to set this equal to 25. All right. So we've made our box somewhere, right? On paper, I just found an empty space. In the array, I found an unused location in the array by checking the valid field. And again, you'll code that up as this function called getNode. So getNode returns the index 4 in this case. If we could not find a space, it's possible that all of these entries are in use. If we go all the way through to entry 99 and they're all marked as valid already, we're out of memory, right? It's just a situation. So in that case, your function getNode, which is saying where can I store my new node, should return this error flag called myNull. And your program that's using that should say, oh, sorry, we're out of memory. Okay, but we're not out of memory. We've got space. So we found a spot to store our 25. We put a 25 there. We called that new. All right, here's the good part. We want to insert this between previous and current. So first of all, let's update the picture. So we want to change this arrow to look like this. In other words, and let me label this as new. In other words, we want to change the next field of previous to have the index of new. Well, previous is 2, so here's the entry corresponding to that previous node. And we want to change its next field to point to new. Well, what's the index of our new node? It's a 4. We just want to change this to a 4. And what does that look like in code? Linked list bracket previous. That's this entry in our array. Dot next. That's the next field. Should equal new. That's not pseudocode, that's actual C code. And if we've marched through and we've got previous and current as the node before and after where we want to insert, and we've got new as the index of our new node, this line of C code changes that arrow to this arrow. It changes that 3 to a 4. And now, as we go through our list from sentinel to 12 to 24, the thing that comes after the 24 is now a 25. So we've done half of our insert. The 25 should be followed by the 30. Well, it's not. We don't know what the next field of this is. What we want to do in our picture is change 25's next field to point to 30. That's the node whose index is current. So we want to take the new node 25 and change its next field to be the index of what we called current, which is a 3. And what does that look like in C? Linked list array indexed at new. That's this entry right here. The next field, which is this block right here, should be set equal to the node whose index is in this variable we called current. And there you go, 2 lines of C. We've inserted a new node. And that's the hardest part of PA1, is doing the insertion of a new node. And it boils down to 2 lines of code. But here's the thing, should this be previous, should this be new, should this come first or last, should this be dot next, should that be new or current or previous, right? Don't try to figure that out from looking at the code. Don't try to get it right by trial and error, right? Start with some kind of picture for what you're trying to do. In our case, our memory is an array, so translate your updates to this picture in terms of operations on this array, and then write code. Right? Once you can do that, you've nailed data structures. Rest of CSE222, pretty simple. The whole challenge in this course is being able to write these 2 lines based on this and this. And it just comes with practice. And eventually, right, this will become second nature. When you see this, you'll be thinking this. And when you're looking at your code and you see this, you'll actually be seeing this in your mind's eye. But it takes time, right? For me, it took, a good month of monkeying with this stuff to be able to get this right and have it make sense. And you'll get it right, you'll get it wrong, you'll get it right twice, you'll get it wrong the 3rd time, you'll get it right 6 or 7 times, and then it'll get wrong again, but it gets better, right? So that's really the essence of what you're after. All right, so let's plow through the rest of the functions we're working for here. So initialize we know about, add we just talked about. So it takes a linked list and an integer, and it adds that integer to the linked list. Print will just take your array for your linked list and just print it out. How do you print it out? Start with element 0's next field. If it's my-null, you're done. Otherwise, it's an index. Go to that entry in your array, print out the data field. Look at the next field. If it's my-null, you're done. Otherwise, it's an index. Go to that element in your array, print it out. Look at the next field. If it's my-null, you're done. Otherwise, it's an index. Go to that element in your array and print it out. We just printed a 25. Look at the next field. If it's my-null, you're done. Otherwise, it's an index. Go to that element in your array is a 3. Print out the data. That's a 30. Look at the next field. If it's my-null, you're done. You're done. And what did you print? 12, 24, 25, 30. So that's called traversing the list. And that's something we do whether we're printing or searching for something or finding a place to add something or finding a node to delete. All right, delete takes a number and removes it from the linked list. And you can assume that this is only called if the number should actually be deleted from the list. All right, and then searches for a list. So traverse the list, but instead of printing, see if you found a number that you're looking for. We'll talk about abstract data types next time. Let's talk quickly about your main program. Your main program is a user interface to manipulating the list. Print out a prompt. Wait for the user to type a command. And the user can type one of a few commands. They can say I followed by a number, which means insert this number into my list. They can say P, which says print the contents of the list. They can say S followed by a number, which says tell me if this number is in the list. They can say D followed by a number, which says delete this number from the list. They can say X to exit. Anything else, give them a help message. If they type I and it's not followed by a legal integer, print out a help message. If they type S or D and it's not followed by a legal integer, print out a help message. So if it's in exactly one of these formats, do what this says. Otherwise, print out a help message. And then, unless they exited, go ahead and print a prompt again, get another command. So start off with an empty list, and the user can add things, delete things, search for things, and so on. And there's details here you should read, right? If the number's already in the list, print out the message node already in list. If there's no space, print out of space. If it succeeds, go ahead and print out success. And I want your program to conform to this exactly, or as exactly as you can. So no extra output, no different wording. Search for a number, the output's either found or not found, uppercase, 1 word or 2 words. Right, so I want you to stick to this. So we'll dig into this more on Monday, but this is enough for you to get going. You can certainly work on your main program, that's CSE224. You can definitely, polish up your init function from the ODP to work for this, and you should be able to start working on doing an add function. And once you've got your add function, the other functions are just subsets of that. So that should be enough to get going. We'll talk more about the main program and the deliverables and the grading rubric on Monday. But I'd say that you've got enough information and know-how now to get 80 or 90% of this done before Monday if you like. So I would urge you to jump into that, try to get as much of this done as possible, and then bring questions to class on Monday. Or office hours Monday morning. Alright, I'll see you in a half hour if you're in 215. Otherwise, have a good rest of the day. Have a great weekend, and I'll see you on Monday.